All right, recording started. Okay, so we have Kevin Kissel from AandB, and he will be talking to us about AandB's approach to hybrid quantum HPC integration. I'll pass it on to you, Kevin.
Thank you very much, Amir. Howdy, folks. So a couple of clarifications I want to make here right up front. First of all, I am going to talk about what we're actively doing at AandB, but AandB is a startup. And a lot of the stuff I'm talking about here is like gleams in our eye of things that we need to do as we intercept HPC with fault-tolerant quantum computing. So what I'm going to present here is to some degree speculative. A lot of this is my thinking, but a good deal of it is also coming from the thinking of some of my physicist colleagues and mathematician colleagues back in Paris, who contributed a certain amount to this. They were, of course, both at the March meeting, so I was, unable to, sit down, at a whiteboard with them on some of this material. So the depth is variable, but I think there's, none of this should be taken to be a rigorous promise of this is what Alice and Bob are going to deliver, with the possible exception of the first slide I'm going to go to after this title splash. But nevertheless, I think it's valid to get the conversation going, and as I'll wrap up at the end, it'll be more clear why I'm doing this the way I'm doing it. So who are Alice and Bob? We're starting to get a bit better known. It's a quirky name. It's a quirky shop. It's a somewhat quirky concept for building a quantum computer, but it's a very powerful one. It's based on the notion of using a dissipative qubit, which is auto-stabilizing on one axis, and one pays a price for that in terms of having a higher error rate on the other axis. We chose, as most people doing this kind of thing do, to use the auto suppression to suppress bit flip errors. And so we have to suppress phase errors otherwise. But having reduced the dimensionality of the problem, everything just gets so much simpler. This is one of these things where, when they were first starting, my intuition was this is a fabulous idea and should be followed up on. Anytime you can offer me exponential advantage for a linear cost as an architect, I'm going to go for it. It is challenging to make these qubits operate correctly, but we're advancing pretty well on this and have been quite successful so far. And to the extent that that building block works, a lot of things fall into place. The required density is lower. The difficulty of the packaging is lower. The dimensionality of the error codes gets lower. So the sketch over on the right is probably not too far off what we can do. Okay, so there's a machine, looks like your basic sort of high-performance server rack, except that we think we can actually get order of 100, probably couple hundred logical qubits into a single system like this without having to solve the intercryostat networking problem, which is always a big deal. Now, to solve the really big problems that we want to attack with these systems, we are going to have to solve that problem. But this advantage that we've got in compactness means that other people are going to be more at the bleeding edge than we are. So we're very happy to see that happening. So that's where we're coming from in all this. And given the fact that, damn it, that was not supposed to be a build. That's the kind of LDPC structure that you can have for if you only need to solve one axis of problems. So instead of having to go to 3D packaging, we're just basically having some shortcuts in the linear snake to achieve what we want to do. But here's the thing. We're planning on delivering fault-tolerant quantum computers in a 2029, 2030 timeframe for the first ones that are actually fully functional and doing useful computation. And this allows us, and maybe even forces us, to take a step back and ask ourselves, what ought we be doing, as opposed to just being caught up in ad hoc decisions. The French phrase "fuite en avant," fleeing forward. So let's think about this for a moment. And these are some assertions that I think we can debate, but I think I have a pretty strong basis for asserting that if I look at a quantum HPC program, if I look at a program which has it may have multiple processes in it, but each of those has a main program that's going to remain classical. And it's going to remain classical because quantum processing is god-awful for doing stuff like parsing arguments and getting system resources and checking security. But a fair amount follows from that, as I'll get into. Quantum information and operations at that classical level of the main program have to be dealt with strictly by reference, which is to say, I've got a pointer, I've got a handle to some quantum state, possibly a collection of quantum state, possibly to an operator on quantum state. But in the classical realm, I can't actually directly manipulate that information. So it's all going to be indirect. It's all going to be by reference. Quantum gates, so far as I can tell, we support, again, this is a term that comes from really more classical computer architecture and quantum, predicated execution, which is to say conditional operations, but not control flow per se. There is no program counter, there is no branch notion, much less the whole notion of the data. The program can be treated as data, as we've had this von Neumann concept that we've been able to exploit in almost all of the classical systems that we've built so far. Quantum state is expensive to maintain. And what by that I mean, even if we have error correction working properly, we're constantly cycling that error correction regime, and we are constantly accumulating some degree of error. Yes, we can stick a lot of nines in there, but we're expending energy and complexity for every additional nine we obtain, and we can never achieve unity. The expression, and so here's another thing, so quantum information, we can express it if it's trivial classically, but there's the well-known explosion that happens exponentially as you try to look at higher order quantum information. The flip side of this, and this is something that people have run into looking at quantum applications, trying to shoehorn quantum processing into data-intensive problems, big data problems like portfolio optimization, or even a lot of AI stuff, is the expression of large volumes of high-precision classical data is very expensive in quantum. I mean, each modality has its advantages, clearly. And so given those things, how we integrate that really sort of from first principles. What does it look like? How do we manage these things? Now, to help our thinking, and this is taking some work that's coming out of the Paris team, we're trying to look at a hierarchy of abstractions here. And some of this stuff is a little odd to me. I'm one of these, minimalist people that thinks that there should be no more abstraction layers than necessary. So this is a topic of active debate, whether all of these are really necessary, but they really all do seem to be somewhat distinct and require researchers and engineers to operate in somewhat different ways. And so the structure of this talk overall is just to sort of dig down through this list, although I'm going to necessarily pay a lot more attention to a few layers than others. Also, the notation I'm using here is something that I've been trying to introduce inside AandB. The original sketches had the much more normal English L1, L2, etc. The only problem was that the level that is labeled here as virtual, the second level above the device layer, got labeled 1.5 very early on in AandB, and I came in, I said, no, you can't have a layer 1.5. That's just too silly. But just so that typographically we can distinguish old and new documents, I'm using this 2L thing instead of L2. Sorry about that. This is AandB history that I should not burden the rest of the world with any more than we absolutely have to. But just to go down through the layer concepts here, application layer is basically, it's how we manage applications. It's making sure that applications get launched, that applications that use quantum get launched in systems that have the quantum resources available to do the job. It is aware of quantum resources. It is managing quantum resources, but it doesn't require and does not have any awareness of actual quantum information flow. Now, the solver level is the level at which people actually write the applications. And here, this is essentially a classical main program, or some depth of subroutine call. It doesn't have to be at the main level, strictly speaking, but at some level of classical structure, we're invoking quantum solvers. And this is classical management of quantum information flow. So I'm a classical HPC guy, and somebody tells me, oh, the best method to do this is to use the quantum processor. It's a little bit weird. Here's the documentation. He sees an API for the function. It's a classical API. He's passing a classical data, but he is invoking the quantum resources, and the person doing this has to have some understanding of the lifetimes of the quantum information. The register level is the level at which one codes the solver. It's a mixture of classical and quantum processing, very much entangled and requiring competence within both. The logical level is the logical qubit abstraction level that we all like to talk about. It's relatively pure, and people use that to express algorithms more than write applications. The virtual level is the kind of tricky one, because to me, it had always been sort of the case where, okay, I build my logical level out of the physical level. But my colleague Ellie assures me that the virtual level is a little bit more subtle than how one usually deals with the physical level, in the sense that there is this odd temporal axis to it that makes the techniques, programs, and abstractions a little bit unique. And I'm willing to concede him the debate. I'll present some material on this in a little bit. This is something I'm happy to discuss and happy to set up conversations with Ellie if we can simplify things any further. But let me take this from the top if I possibly could. So at the application layer, we just have to know that certain applications have quantum requirements and certain don't. So the OS needs to reason about those resources without knowing what's going to be done with it, which is completely normal. It's as if you needed a GPU. It's as if you needed a floating point unit in the old days. And then how we do this is shaped by some of the odd rules of quantum information. There's, the no copy rule means a bunch of stuff. We cannot just preempt and reschedule them. We cannot copy the information for a checkpoint restart. It's set it up, run, and if you got to do it again, you got to do it again. But if you're doing it again, you're doing it from the beginning. And so to be efficient with our resources, and particularly to be efficient with the classical resources, is a big deal for a lot of us here in this group. Is, how can we make sure we're not wasting or stranding the classical resources that are used from time to time during this hybrid job? We need good quantum resource estimation. It doesn't have to be perfect, but for every 9 we can get out of it, that's greater efficiency that we can have in our resource allocation. And a comment here at the end, and this is getting at something we've been discussing off and on in this group, the classical components of the computation can and probably should be run in distinct processes in the strict sense of a computer process. And those processes may or may not be physically co-located with the quantum processor, but depending on what you're doing, they had better be close. But logically decoupling the classical and quantum computation gives us a lot of flexibility in terms of how we manage things. So some folks have seen variations on this slide before, but sort of a first step in how thinking this stuff through, and this is going back months and months, is the notion that okay, today we're essentially operating directly or fantasizing that we're operating directly a quantum processor from some kind of workstation, may have GPUs, and what we've been learning to do is how to take that from an interactive operation where we're connecting to a front-end CPU, either directly or across some API across a cloud, running our stuff, getting it back, saving it, processing, doing whatever, to something that we can actually use in more of a simulation campaign style. And that's how it's going to be batch. And this is, again, a lot of people working on this. This is, why Slurm integration is important. This is why we're looking at, flux integration and other things, is that this has to be part of the tool set we're using in our clusters. If I step away from the current reality that quantum processors are very scarce, very limited, and very expensive, and I'm just looking at this as a guy who's, architecting computing systems. It's like, oh, I have a specialized processor. It has its quirks. Sometimes I'm going to need more classical than quantum in a processing pipeline and a simulation pipeline, for the sake of the argument. Sometimes I'm going to need more quantum than classical. It all has to do with how many cycles and the relative speeds of these things. So we ought to have tools and ways of thinking that let us relatively naturally scale either way, depending on how things turn out, depending on the properties of the particular quantum processor that we have in our shop versus the other guy's shop, or the number of GPUs that we have in our shop versus the other guy's shop. In any case, this is going to be driven by people launching classical programs in this HPC cluster. Another aspect of this, which I think is pretty important as we advance, and I think we're at a cusp now where we really need to start reasoning about this, we haven't started to think about yet, is this notion of decentralized control as the thing is executing. If I look at how I run an HPC program, how HPC programs get run today in general, not only are they being run in a sort of controlled batch manner as you're sweeping your sets of parameters or whatever, but the programs themselves, to the extent that they're using different resources or operating in different phases, tend to pipeline, and they tend to pretty much self-synchronize, this sort of loosely synchronous model that we've been using in parallel processing for a long time. The above diagram is a lot like what I think is going on today. Essentially, somebody has a login node, they have their workstation. Here I've got this thing coded as if it was some form of C++, so they're probably actually writing stuff in Python here. And so you're calling some NumPy functions. You're calling quantum server calling with quantum, sort of send your quantum program. You're getting the data back from the quantum solver using Qiskit or whatever, some gasket that's getting me to a remote machine. Then I'm going to invoke some classical processing later. And so as you can see, there's an awful lot of communication that's going on back and forth. There's an awful lot of synchronization that's implicit in that model. And what I think we want to get to is a model where the programs are far more self-timed, where I basically launch that program on some specified number of nodes. It wakes up on that number of nodes, and by virtue of the same program and the same set of parameters being visible to all the nodes, they self-organize. So the quantum part says, oh, I don't start until I get my inputs from the pre-processing process. And so it waits on MPI messages. Once it's got its data, it computes. When it completes, it knows that it's supposed to send its results, the measurement, discrete or collection of measurements, via MPI to another process that's going to be doing the post-processing. And those pre-processing, post-processing, they might be parallel, they might not. It's not important. The important thing is that we're getting away from having a central timekeeper for the operation of each of these things, because we want a number of these to be flowing at once. And so my hypothesis here is that at some level, we're going to have hybrid binaries. So we have classical source code, we got quantum source code. We are probably going to have program files, individual input files that have both mixed classical and quantum. Those are all going to get compiled, and the compilation is going to generate classical binary code, and it's going to generate quantum code in some relatively high level representation. It may be a basic block of gates. It may be some form of representing ZX relationships, not entirely clear. There's a dotted line that's on there from you're looking at the flow in the center between the two, which is to say the classical binary sections has to know about at least the identities, the signatures of the quantum blocks, because it's going to be responsible for running them. So that's why there's a dotted line there, and there's a dotted line in this hybrid quantum binary file sketch. Now, that quantum binary file might be something that is actually a set of indirections. It could be a file that contains other file names, but for the purposes of distribution in a cluster, it's actually kind of nice if it's not indirect. If by distributing the quote-unquote binary, I actually am distributing both the classical code sections and the quantum execution blocks. And those go off into storage in my cluster. They get pulled in by various machines. And here you've got a sketch. The same binary is being grabbed by a machine that has no quantum support, that has no classical support, that has quantum and classical support both. And it can determine its role in the program based on the resources that it sees available on the platform and the configuration it was given at its launch time. So that's all happening at what I'm referring to here as the application layer, as we're dispatching the applications. But we have to write those things, okay? So those applications are going to get written at a solver level. This is going to, again, largely be classical logic, but there's going to be some quantum logic involved because we have to understand what the quantum stuff is going to have to do. So example over here on the right, this is just somebody's simple example of how you would actually do Shor. And again, that's all classical code. The only thing that it is doing, it is invoking a quantum solver that was passed in. And furthermore, it's invoking it using nothing but classical inputs and getting classical outputs out. This is sort of again, this is out of the literature, but this is just sort of the canonical sort of solver level way of writing code. It requires it requires high competence on the classical HPC side and some understanding of what can be done on the quantum side. And again, anything that's being done in quantum is being handled by a reference here. And if I then, based on some of those hypotheses, drill down a little bit on how I might build a hybrid quantum binary for HPC, here I'm imagining this as an extension of GNU, Linux, ELF, because that's the world that I came out of. I'm used to hacking up compilers and doing oddball stuff like this because, the Linux loader and tools are incredibly general and powerful, and being able to leverage that stuff is just a blessing. So a lot of stuff just works. So, the notion here is if I'm building my solver, I end up something that ends up being, it's an SO file. And the only thing that I've done to it, other than having some code and some entry points and some references, is I've got a symbol that gets me, or maybe several symbols that get me to blocks of quantum code. expressed in some reasonable way, binary way, that has been generated by my quantum compiler. And so they are labeled, and the classical glue knows to do so. For example, if I'm calling one of those functions, like I alluded to previously, in this case, it was an indirect, so it's passed in the address of the function. That classical function gets called, and it schedules the quantum basic blocks to be executed on the quantum hardware. And again, so here's this notion that I'm building this thing. I have a single binary that has all of the core code, the main code in it, and then it's linked to a bunch of shared libraries, some of which are classical numerical libraries, some of which are quantum basic blocks. Now, they're all in the binary because that binary is sort of a universal thing, but that does not necessarily mean that everything gets executed everywhere, as I mentioned earlier. And frankly, as we prototype this stuff, because I asked myself the question, how can I demonstrate this? The quantum basic blocks that I generate in the earliest prototypes are probably actually going to be Python modules that will themselves then recursively compile something and run it in a simulator on a device. That's not efficient, but that's not the point. I'm trying to basically get the structure right. So again, the evolution and one of the separation of processes here, and this is not something I've not discussed very much. It hasn't been talked about very much, but this is something I would really love for people on this call to reflect on a little bit. So let's suppose I have a quantum processor and it's got a bunch of cores on its classical CPU that's on the front end. So there's no reason why I wouldn't be able to do the limited amount of classical processing that has to be done in association with this job locally on that machine. Fine. And again, for variational algorithms, and I'm not focused on variational algorithms personally because those are much more a NISQ phenomenon than a fault tolerant. Variational is hard in fault tolerance, just not a great match, as most of you know. But so let's assuming I was doing something, variational here. I could do it all in a single process. But by separating things out, by having one process on the front end that owns the quantum resources and is only running the quantum blocks and is communicating to another process, it's the same machine, it's in memory, it's extremely efficient, but I'm using message passing to get to the classical process. So why would I bother doing that? Well, that gets back to this question that we've had of how do we not strand resources? If I know the time that it's going to take for that quantum processing to happen, I can deschedule that quantum process and have those resources do anything else up until that magical time t. If I even have an approximate notion of time t, I can play games and liberate those resources in a way that I could not if it were a single process. And then, of course, there's also the whole notion of that process ends up being a preemptible process. It may be that, in fact, I'm going to send the MPI message to the classical process, which is, in fact, asleep, and I'll have to wake it up and allocate it stuff. That will take hundreds of microseconds, possibly milliseconds to achieve, but that may be less than the slop it would take for me to try to schedule things if I don't know how long it's going to take. We have a lot of options here, but in separating the processes makes it easier to control the resources. That's the key to this observation. And having done this, having made that step that the classical processing is now happening in a different process, it ceases to matter whether that process is a single process or a collection of processes, whether that process is a process on the front end or on some other compute node on an HPC cluster. Again, we're adding a little bit of complexity, but that small amount of complexity opens a lot of doors for cool things that we can do. So operating at the register level, okay, this is a little bit different. Here we actually really do have to have some competence at knowing what we're doing in quantum, because we're really implementing these quantum algorithms and mixtures of quantum algorithms with classical control. So this is, I think I made the comment here, the users don't need a deep understanding of the quantum algorithms, but the writers do. The main language I'm familiar with that was sort of targeted at this level is Q#, which has its advantages and disadvantages. But that's sort of why I use the example here, because again, at this level of programming, it seems to be a pretty good abstraction. I don't know if it's going to dominate. People use things like chasm up and down the line, but these things become hacks, and certain details at certain levels tend to bleed. So it's kind of interesting noting when people have come up with tools that are particularly well adapted to certain levels here. And then at the next level, we're really the logical level. This is what we're talking about: logical qubits, logical operations. Here, I personally think that we're really interested in formalisms. I think we're really interested in being able to do proofs. I think this is the level at which we want to be able to set limits in terms of resource allocations, minima and maxima, things like this. So we're talking about, idealized qubits. We are talking about idealized operations, and some of which may, and again, some of which may not actually be possible at the physical level that we have to emulate. For Alice and Bob, this is more clear than it is for some other folks, just due to our technology, which I'll hopefully touch on in just a moment here. But again, one of the things, human efficient representations is a topic of serious research. And this is one of the reasons why, I love the work that Santiago has been doing in terms of looking at, can we have a clean looking quantum virtual machine that actually looks as a good abstraction for this? I personally think the ZX calculus is fascinating. And I've been exposed to category theory going back 40 years when a buddy of mine in a chip shop was trying to build a category theory based chip database. It was really difficult, but we learned a lot of stuff. It looks pretty. It's hard as hell to code. Human efficient representations here are a challenge, and I think and human interface tech is not something to be belittled as we try to deliver on the promise of what we're doing here. At the virtual level, and this is where, Ellie really feels very strong, it's not quite physical for a couple of reasons. One is that while it is operating on physical qubits, it's also operating in a temporal domain where you're going back into time looking at previous measurements in a way that one really doesn't normally do in the formalisms that I've seen to describe physical qubits. So, and here the folks at I believe it was Google came up with this, again, yet another language, STEM, which is all about doing specifically this. And so if a level develops an application specific language, maybe it has an identity. Maybe it's not just a 1.5. Topic for debate, and something I would love, for our folks to engage with folks on this call to talk about. But Ellie's main point is there is this additional temporal dimension to everything that's going on that one doesn't see at the levels below, and nor above. And the diagram in the middle here, this is actually an example of from one of our papers of how we could implement a fault tolerant operation using a finite state automata code that we published. And finally, we get down to a physical level, where really it gets down to we have to make the quantum information dance one way or the other. In the case of cat qubits, it's kind of peculiar. What we have to do for CZs is pretty weird, but we can do them. And so here people tend to reason typically in gates. And again, you'll see openQSE all the way up and down these layers. So you'll see openQSE working at this layer. But I would make a point here that whereas at the logical level, I can basically put some restrictions on what I'm going to be able to do in terms of which axes I can do my rotations on, or what granularity I can do the axes to some number of very precise number of bits as a fixed point value of radians or whatever the rotations I'm going to do. At the physical level, I really want to get as close as I can to analog in this while remaining digital. So you're going to be seeing floating point values where you might not otherwise need them, and a different system. And then how one reasons about measurement, whether one is allowed to reason about measurement within the scope of a program, is a question of philosophy and a question of tooling. And it's very clear to us at Alice and Bob that the logical gate set and the physical gate set need not be the same thing, because in our particular case, they cannot be the same thing. There is no native Hadamard in a bosonic dissipation cat qubit. We can create it as a logical gate and have done so, but we've got no physical Hadamard. And so that fact really forces us to understand that these are really two distinct abstractions, possibly requiring two distinct languages. So anyway, that's diving down. I'm not going to go into the device level here. God knows I've taken enough of your time, but hopefully there's been some thoughts here. But again, just given that this creates almost as many questions as it answers. One question that is a topic of active debate is, as we are compiling these binaries that I described, to what level do we do the quantum compilation? My personal original intuition was that, oh, we're compiling to the logical level. Now, why would we compile to the logical level? Well, for one thing, it means I can run the same binary on very different quantum machines. That seems to be a virtue right there. And if we're in a world where people are selling commercial shrink-wrapped applications, that actually is a big deal. For the people supporting an application, have a single binary to debug, ship, and support is huge. And if it fails on a platform and not on the others, that basically helps identify where the problem is and will lead to a solution. So that's just this very nice compile to logical run anywhere. But at the same time, we are looking at some error correction schemes, and particularly I'm thinking of the ones that aren't Alice and Bob's, because we have a big advantage in terms of having lower overhead, but the overhead is real for us nevertheless, and so that overhead we want to incur as little of that as runtime as possible. So it really gets down to the question of how much of the error corrected operation can we generate as code at compile time and make that as a binary compiling the physical. Now, my intuition is that that's going to be restricted. It won't be as efficient in terms of what it can do. It will take up more storage, but it's a completely legitimate path, and I don't think we know enough to know which is actually going to be the best path to take pragmatically to use these devices for research. And another conversation that's been going on in this community and very actively that I think bears touching on here is we've been talking about, oh, let's use HPC resources to do various things, whether it's to do the error decoding or to do the computation or somewhere in between. And all of these are reasonable. All of these have separate constraints. And one of the reasons I think it's appropriate to be a little bit proactive in thinking through at what level am I operating when I'm doing these things is they could all be happening at once. And if they are all happening at once, it should be invisible at each level what's going on. In other words, if I'm using some GPUs in the cluster to do some kind of AI enhanced decoding scheme at the virtual level, and I also happen to be invoking some GPU-based classical solver within my solver code that I'm at the application, and if the application is also using a bunch of CPUs to do some parallel computation within the cluster, those allocations are happening at separate levels to separate logical users. Well, actually, the application of the solver uses the same user, but that virtual level stuff, that's system resource, essentially, that's being allocated. So, keeping this stuff straight in our heads will allow us to do a better job of parallelizing and not tripping over ourselves. That's an assertion, not a provable fact. So why am I giving this whole narrative here? Well, really, we are a small shop. We got some really good ideas. We got some really good people, but we do not have the delusions of grandeur that believe that we can actually develop on our own the best in-class set of tooling and operational stack for fault-tolerant QC and HPC. So I'm putting these ideas out here just to see if they resonate with you, see if you have strong counter arguments. Fascinated to hear that. Those of you with whom this resonates and you're saying, yeah, this is the kind of stuff we ought to be building, you don't have to raise your hands now, but drop me a line. I mean, we are really trying to find people we can work with. We can try to find the tooling that we can integrate with the minimum amount of mess, the minimum amount of effort, so that we as Alice and Bob have a strong stack that we can deliver, and so the community has a strong set of tools that we can advance the whole field with. We're working on a white paper on this. In fact, this talk started out as, oh, I'll finish the white paper and then I'll do a talk for the openQSE team, but time didn't permit completion of the paper, so this presentation got out a bit ahead of it, hence the variable level of depth. So on that, thank you very much for your attention, and I am thankful that I'm actually on the other side of the screen so that actually thrown objects won't hit me.
Thanks, Kevin. I guess we're going to open it for questions. Please raise your hand if you have some. I have some, but I'll wait for people. Go ahead, Santiago.
Karen, thank you. This is a great presentation. I'll reduce to one priority question I have. In an HPC facility, we have multi-tenancy. We have multiple users trying to use the system at the same time. This is different from treating a QPU as a telescope, where you just send a batch job, something executes, and you get something roasted after the process. I was thinking, although QPU jobs are not exactly preemptible, when you think of a job as a collection of, let's say, the specification of a program equals circuit plus a number of shots, something we've been thinking about is, what if we could, for the same program, separate the number of shots and do sub-jobs? Have you thought about something like that? Or where do you see bottlenecks
clearly.
arising?
I mean, that is a thing. I mean, again, the only thing that's atomic is a shot. The only thing that's truly atomic is a shot, okay? That having been said, and actually, once we're in a fault-tolerant regime, I think that becomes a strong statement. It is not a strong statement today, because if the calibration drift is unknowable between shots, it's harder to do the post-processing. If you follow me, this was an issue at Google. In other words, if you were doing a run, you wanted to do it within a certain window of time after the last calibration, so that you're comparing apples to apples when you're comparing runs. And so, but in a fault tolerant situation, no, the only thing that is atomic is a shot. Yeah.
Okay. Thanks so much.
And one of the questions, so I'll return a question to you, because this is one that I didn't ask here, but this is a great audience for it, and you're a great person for it, is if I am, when I make the request of the quantum device, at a minimum, I have to ask that it does a shot, because that's atomic, and then, any measurements that result from that shot. Okay, fine, that's a thing. But do I want to make it a thing to do a bunch of shots, so that what is returned isn't a set of measurements, but a set of vectors of measurements? And because that whole notion of operating in collectives, it's a common, thought pattern. It reduces the number of interactions with the quantum device, but it also creates a much larger window of atomicity that we have to respect. And so to me, it's really not clear what we want to do. I mean, it's clear that we must do a shot as an atomic thing. And then do we support collectives? I mean, again, we're recapitulating classical. To what degree does it make sense to have a parallel, do this multiple times instruction as opposed to write a loop? And the answer to that depends on the implementation technology and the rest of the architecture. So I expect it's going to be similar here.
No, thank you. One last comment is that here we've been thinking about that there's a similar model to latency. There's a cost of starting a quantum process, and there's a cost of repeating. So we need to think about these things. Yeah. Thank you so much, Kevin.
Lee, looks like you're next. It also looks like you're muted.
Oh, sorry about that. Thanks very much, Kevin. That was a great talk. I'm curious as well. I also come from the perspective of classical and quantum code needs to be built and generated in a single, compiled binary. How you get there, obviously, is, there's many discussions to be had on that. But I do see a lot of overlaps here with the type of support we have in our infrastructure already with the LLVM MLIR-based compilation ecosystem, as well as what you're kind of looking for here. I'm just throwing this out there as, hey, this might actually be an interesting thing to see if that type of infrastructure meets your needs.
Yeah, so it might. This is absolutely a conversation to have with some of my colleagues.
Great. Yeah. What I'll do is I'll maybe ping you on Slack and see if we can kick something off.
Please do.
Cheers.
Free clue. I'm flying to Paris tomorrow, so I'll finally be in the same room at a whiteboard with some of my collaborators, and so this will be a good opportunity to get your questions into me in the next few days, is what I'm saying.
Sounds good.
I can't see who's number one.
Hey, Kevin, this is Yogesh here. Couple of quick questions. So one of your slides, I think slide 6, you had a couple of patterns in terms of quantum plus HPC interactions, right? So I'm just wondering if you have identified other kinds of patterns of how applications would sort of flow between quantum and classical, because this is one of the other working groups we are working on the system integration. We're looking to see what kinds of these workflows you would encounter. So do you have any additional such patterns that you started putting together? Right?
No, to be honest, no. I mean, we've imagined many things. It's, this having a good imagination is a blessing and a curse, right? It gives you really large universes that you have to explore, and sometimes that's hard work. But no, the point I want to get to is I've been approaching this as I learned to approach other kinds of integration of new concepts in classical, because I did that a couple of times, and that is really ask what is fundamental, fine-grained, enable the most aggressive thing that I can imagine, and find a way that it's not expensive to do the most aggressive thing that I can imagine, and then the less aggressive things fall into place. So in my mental model of a 2035 HPC program, somebody is modeling some complex multiphysics system. And some of the subsystems that they are modeling are more efficient, most efficiently modeled, or the only way we can model them is to use a quantum processor. But that's part of a big multiphysics job. And so those modules are going to be written to use a quantum processor. There's going to be other modules. How many processes in this whole thing running, each process is going to be replicated probably across thousands of cores, et cetera, in this big flow, it's going to look like that. Okay. So what's going to limit what we can do? What's going to limit is a couple things. There's going to be what limits the long side. How big a quantum computation can we do? And that's going to be limited by how good is our fault tolerance and how good is our fundamental qubit technology. And then the flip side is how short a quantum computation can I do and still have it be efficient? And that's where I think the interesting technological challenges and architectural challenges will be. But my model is it's N to M and then back to M, and N to M to O to P, fanning out, phoning in, spinning, like any kind of complex computation you can imagine. The reality is that almost everything will be simpler than that, but it won't be trivial either. And we don't know what the simple patterns are yet because we haven't done enough of this stuff. So my attitude is enable a large universe, pay attention to what we're doing, and optimize for what we really do.
Gotcha. One quick, maybe this is more of a comment. It's a bit more philosophical in terms of decentralized control, right? Versus centralized. I'm a big fan of decentralized, but in practice, it's very hard to implement, right? Fault tolerance is one example, scheduling is another, and so on, right? So one is having centralized control, but with decentralized data flows, right? But control is centralized, but data flows are decentralized, right? So just wanted to see if you had given some thought on that.
Yeah, I hear what you're saying. Now, you folks probably can't tell, but there's a gentleman with a leaf blower that is just outside the window. And I can, even with these earbuds in, I could barely hear you, but I think I did understand your question. And yeah, no, it's a good point. No, one assumes if you're going to do distributed control, you have to assume that you're running on already what has been built to be a robust system. But which is what we're typically doing in an HPC center. I mean, good put is never 100%. That's our dirty little secret. But yes, this does presuppose some level of reliability. And I guess I could say philosophically, it is always hybrid control, because that centralized control I described, well, that distributed control is executing a plan that was delivered in a centralized manner because it was critical that everyone have the same plan. Now, is that plan dynamic? Maybe. Was that plan determined when I first compiled the job 6 months ago? Or was it determined by the launcher, on the basis of parameters that it can get at the time? Maybe. My first prototype is going to be pretty freaking static because that's not the point here. But no, do you understand what I'm trying to say here? Make it possible and then determine what is efficient.
Absolutely. Thank you.
Hey, Kevin, so if you go back to the NPI, one of the NPI diagrams that you had where you have like data flow between the NPI and the quantum computer, like the separation of processes.
Yeah.
I just had a question there. In your mind, what are you thinking that classical processes are in those diagrams? Are they something that is QPU specific, like short classical processes that are required by the quantum computer to enhance error decoding or something like that? Or is it something extra, something related to the larger simulation run?
I think the answer there I can say confidently is yes. Which is to say both probably. I mean, no, again, an interesting question, how extreme one wants to be. If there's any, to my mind, I was actually thinking more in the case of the, how it sounds insane to talk about traditional quantum computing, okay? But if I look at a traditional variational model of quantum computing where people really are, the amount of compute isn't huge typically, but it has to be done relatively quickly and in conjunction and fed back into the program. It's a short feedback loop. So to my mind, so that's where the notion is, and this is where various folks have argued that no, serious, got, single process on the same machine, otherwise we can't make it. My assertion is same machine, yeah, maybe, but not necessarily the same process, and separating the process gives us a better handle on the resources. So to my mind, initially, it's like, yeah, this is where I'm running the classical side of the VQM iterations, and probably the control loop as well. But it really gets down to the question of what must I have in that QPU process? The only thing I must have is the sequencing of blocks. And here's my gate to fire that block, and my inputs, here's my outputs going out. That's all it actually has to know, is basically sort of the MPI endpoints to the exchange. That's probably being too extreme. So, I think some amount of housekeeping and stuff should be done in that quantum focused process. But the idea here would be to have as much of the classical process, and especially of the application part of the classical application part, in that separate, essentially classical only process that's on the same machine. And again, possibly, communicating with shared memory. So this is going to be really quick. It's not zero overhead, but it's so close that in the time scales we're dealing in, I think we're fine, and the control that it gives us is worth it. But again, that's my gut feel as a systems architect, and reasonable people can disagree, and well-conceived experiments and data trump my intuition every time.
I think the only thing is, as we move towards quantum fault tolerance, it seems like the sentiment is that quantum processes are going to be such a long running processes, or long running on the quantum machine, that it becomes questionable whether you want this feedback loop between the process, unless the classical code is again in support of the quantum process, like error decoding and stuff like that. But if it is part of the simulation,
in the longer term, we will probably see less of that. In the longer term, we're going to have multiple quantum nodes that are going to be connected both by quantum and classical networks. And it's going to get, it's going to be a more complicated composition. And again, having the ability to do distributed control and distributed computation in a quantum application becomes even more important in that case. No, but I agree with you that, we are now in a phase where that model makes sense. Having code systems that support that model will make it easier to get to the model where, it's off running for a month, and it's going to send us a message when it's done. And yes, it may take me 5 seconds to spin up the process that it woke up, because that process has been asleep for a month. But 5-10 seconds after a month as a percentage is in the noise so far down that I don't care. And that's the other thing. At some point, we just say screw it. Yes, we tend like to have in HPC clusters, tend to have nodes that are dedicated to a job at a point in time, because anything else is just creating noise in the timing. I absolutely get that. But I've also been in a fair number of, yes, very true, Santiago. And this is why, it's like too many levels. We got to get rid of one. But every time I try to kill one, somebody comes up with a good reason why they still exist. So again, another conversation. You've met Ellie. A conversation to drag you into with Ellie. But getting back to what you were saying there, Amir. It's more of a that phenomenon, that co-placement is more of a near-term thing, is what I had in mind. It's basically, but it's a path to get there. The other thing is, if it's really going to run for months, well, let me put it this way: if it's going to run for months on an Alice and Bob machine, it's going to run for centuries on a cold atom device. And so, our algorithms will get more efficient, I swear. But again, we're going to have these basic blocks that are atomic, and we can't run any less. And making those small and making the machines execute them efficiently is our job for the next 20 years.
And to support your point, I've heard a talk just recently that says some algorithm might actually utilize short circuits just to have 1 to 2% more efficient accuracy over a classical algorithm. So you already get to a classical, to an efficient result using classical, and then you add this 1 to 2%, which might fit in that particular.
Yeah. It's part of that. It's absolutely part of that universe.
Go ahead. Sorry. Spencer.
Oh yeah, thank you so much. This was super clearly laid out. I did have one thing stood out to me when you mentioned that you were thinking that a QPU like program should be agnostic after compilation. Like if we have a hybrid blob, your perspective was QPU maybe should be left, like compilation should be left to the vendors after submission, but that's not done with CPU or GPU. And it kind
It
of
is
stood
and
out
it
to
isn't.
me. And
Now,
I wanted
now careful. I said it should be
yeah.
possible. I didn't say it should be done.
What's your
No, I mean,
reason
okay,
behind
yeah.
that?
You seem like a charming young guy, so you probably don't remember Pascal and P code, for example. So no, there was a time when there was a programming language, Pascal, nice language, nicely structured, kind of a language. It would look very familiar to you. It had a lot of influence on a lot of other languages that you've probably seen, but the compilers simply generated P code, which was an intermediate code that was interpreted. Okay, and so and Java, similar thing, Java bytecodes. Okay, so I mean, we have this metaphorical model, but again, implicit in what I hear a lot of people saying these days is there is a desire to compile to a common, relatively high intermediate level, because among other things, that actually allows us to do optimizations at a level that benefits everybody. So you sort of have your fairly specific optimizations at some level. And this is what we do classically anyway, right? At some point we unroll loops, we do all kinds of stuff that is completely architecture independent in the early phases of the compiler, and then it's really at the back end where we're down to say, oh, it's Intel, and furthermore, it's this generation of Intel where this is the right trade-off to make when I'm generating the code. It does that. Now it's doing all of that at compile time. Whereas, for example, if you are running Java, then it would have compiled the main structure at down to bytecodes, but then that bytecode interpretation by the little Java virtual machine would have been built to use the right operations for that processor. And so, I mean, God knows we can do that. And that's what I see a lot of people leaning towards. And I like it as a thing that we do early, just because of the independence, just because it's like somebody else's program from somebody else's project can come in. I can just import that and with a few shims, try that out on my platform without having to have his source code. That's fabulous. But I also know from experience that in the classical world, we had a lot of generations of doing weird trade-offs between what you do at compile time and what you do at runtime. And some counterintuitive things happened. And so I am probably the only, I don't know if the other guys at AandB, who are really more physicists who tend to think of time as this independent axis, and so it doesn't really matter. If I'm talking about this stuff, it's like, when is it going to happen? And they'll say, well, we want it to be done as early as possible, but as late as possible at the same time. Yes, but what does that mean? And so, no, that's what we have to explore, Spencer. But again, good question, but I think that's where we're going.
Oh, great. Thank you. Yeah.
Yeah, I guess related to that, you mentioned before that you'll have one binary with both classical and quantum compiled, and the quantum would be compiled to some logical level, right?
Or possibly all the way down. It would just be bigger and also more platform specific. And that's the annoying thing. I have to have, there's also version control that we have to worry about here, right? If I have to compile a separate binary for every actual physical quantum device that I might be targeting, I got to generate a lot of binaries, and then when I'm running, I got to make sure I pull. I mean, it's not hard. It's just more stuff that we got to do in managing the systems.
My question, though, is for the quantum device, even the same quantum device over time, from what I understand, and this is the question, it drifts, and then you will need to recompile at some point to be able to optimize for those, the new calibration that happened or whatever. So that's the question. Are we always going to have that?
And this is one of the reasons why some of those ideas in the classical world for compiling like excessive knowledge into the binary didn't catch on very well. Because, then people got the next generation machine, and it's like, wait a minute, now I'm no longer 99% efficient. I'm only 86% efficient. What the hell happened here? How do I fix this? And and then you're told, no, it's a feature. It's a good point you're making there. Absolutely, it is a concern. We have, it's something we have to watch.
Go ahead, Sandeep.
One of the sources of friction I am most concerned about is the proliferation of independent pieces of software in HPC QPU integration. If we look at the resulting diagrams, we find a potpourri, or we find a collection of things that are purported to be needed. The actual concern is for adoption in HPC centers. At some point, you will have a human, and you will have that human is going to be a systems administrator, a systems manager that will feel a bit more concerned managing all that complexity. Where do you see it? How can we prevent that from happening based on what you've shown here? Or is there a minimal complexity that is unavoidable? And what,
Yeah.
How do we?
I'm in one of those weird positions where I assert that there is a minimal complexity, but I have no idea how to find it. Which I think we run into from time to time in this world. But what I would recommend, and I would look, and again, we must not mistake, not everything in quantum maps perfectly to things that we've done in classical. But in terms of how we think about integrating new technology and managing computations with a new technology, we've seen this problem before. So the thing that we have did in classical, and this is basically an awful lot of, the advantage, people underestimate both the amount of work and the amount of benefit that came out of the whole GNU Linux effort. I mean, people say, oh yeah, everything's running Linux. Yeah, well, that's nice. No, but what we did in terms of like compilers and tools and all kinds of stuff that came out of this was incredibly powerful. And when we were building new classical processors, one of the things that we did, because it was necessary to sell a new classical processor, if I go back 20 years, was that you needed to be able to deliver, a full chain, prove the existence of a full chain of building from concept to binary running on the physical machine. So you needed the operating system, you needed the runtime, you needed the compilers, you needed, if there were like custom libraries for that architecture to implement its advantage, you needed all that stuff. And so you needed everything on that path. And so it may be that you would like take the entire open source universe and say, that's huge. But what do I need to have a place to stand? What do I need to give a customer, to give a user, so that they have a place to stand? And again, because the classical world, we were all in agreement. I mean, it sounds weird because, come on, we're still talking about registers that have, arbitrary sizes for quantum computing. The reality is going to be at some point that registers are going to have natural sizes in quantum computers just as they did in classical computers. It's not that because we like it, it's because addressing is too complicated if you try to handle everything by a bit address. That's what it gets down to. You don't want to throw bit addresses everywhere in your wiring. How can I aggregate things in a way that I can operate things efficiently? And we hit on a number and it became 8, and then multiples of 8, 32s and 64s. We did that kind of, we aren't there yet, in the classical sense, but I think what we do is we identify, and I think this is part of what this whole team is about. We're trying to identify a tool chain and a runtime stack that is open sourced, that is useful for integrating HPC and quantum. And we should encourage, it takes effort. If we're discovering that, oh yeah, we're using this all works because we're using, 600 different weird packages. Okay, of those 600 kind of weird packages, how many things are we using one trivial function from that package because that's what the author knew to use at the time? And the answer is a large number. And having done this myself, I hate to say it, but you roll up your goddamn sleeves and you code into the main body of work what you're using, and just have a project to eliminate dependencies. It just becomes an objective. It's not the kind of shit that gets you promoted at Google, but it's the kind of stuff that you got to do, just to ruthlessly simplify and get rid of dependencies. It takes an active effort. So we're running as fast as we can just to seem to stand still with all the shit going on. And so, yeah, we're using any tool we can get our hands on, but we're going to have to clean up the mess. And it's going to be somebody's job, so it becomes everybody's job. Okay, and end of my rant on that. But that's how I see it anyway.